intervals of increase and decrease. Now this chapter slowly sneaks up on you. 5.1 and 5.2, at the end of those two, you might be like, this is great. Love all this stuff. And then it'll really dig in. So if you don't really get 5.1 and 5.2 when you get to those other parts, it can cause you trouble, right? But if at the end of this lesson you're like, oh, you can put that in the chapter 4 test. I already sort of know all this stuff, then that's great. Recall the following definition. Yours doesn't start there, does it? Yours starts with am I wrong? Doesn't yours start with a different sentence? Starts with that, does it? Yeah. All right. Huh. Intervals of increase and decrease. We now return to analyzing functions. When I say return to them, when we left analyzing functions behind and got distracted by the derivative, what we were doing was using vertical asymptotes and horizontal asymptotes and end behavior to graph crazy functions. That's where we were at during advanced functions. Then we stopped doing that at the end of Unit 5 when we got distracted by trig. Then we came back here and I did rate of change for a while. But to be clear about where we were at with graphing functions, there was a very unsatisfying part to the whole thing. We got the shape and then there'd be a max or a min and you're like, oh, where do we put the max or min? And the lessons basically told you, well, don't worry about the max or min, just show that there is a max or min there. We won't be able to find that specific max or min till today. Now we'll be able to find all the max and mins easily. No complete the square nonsense. Bang. Get maxes and mins like that. We've got the weapons now available. So in this lesson, we'll investigate the intervals of increase and decrease of a function, and then apply the derivative to easily find the intervals of increase and decrease. And by the end of the lesson, max and min will be laying right there. It'll be like, isn't that just max and min right there? That'll be this afternoon. This afternoon, I'll turn around and go, okay, let's get the maxes and mins. Review. Intervals of increase and decrease. In simple terms, a section of a function is increasing if it's going up. Hopefully that's not confusing anymore. It is to the grade 9s because when I put my arm up like that, or I draw a line and say, oh, that's going up, they go, well, yeah, but it's going down this way. Because they don't have all the technical experience you have to say, well, usually when we left to right is time, right? So left to right means this is up, even though I know that's down. So this is, we say up, and this is, we say down. We won't get hung up on the relative meaning of up and down. We'll just say, okay, increasing, decreasing. This leads to saying the function is decreasing, a section is going up. Are you thinking tangent slope? Well, I hope so. In the middle of all this, we've been tangent slope, tangent slope, tangent slope. Tangent slope, positive slope, going down, decreasing, negative tangent slope. Derivative positive, derivative negative. If after all this that we've been working on, you're like, that's it? Actually, yeah. There's some nice things about calculus. The algebra in calculus is horrific. You've been finding that out. Some of the algebraic and geometric implications here, there's all sorts of stuff to know from previous grades and tying stuff all together. But the calculus is beautiful. The calculus says when the derivative is positive, we're going up. When the derivative is negative, we're going down. That's simpler. This is pretty simple from a concept point of view. I put that right in the notes. But it can lead to some nasty algebra, which we've already found out about nasty algebra. Here's the pictures from advanced functions that seemed difficult at the time. Increasing means the y values will be going up when the x values are going up. Decreasing means the y values will be going down when the x values are going up. Yeah? Just the fancy notation, that's all. Which at the time was like, what are you talking about? But now with a little more experience, hopefully these aren't too bad. So using the derivative, do you see where this is going? I hope so. I've tried to lay it right out there. If a function is increasing, the tangent slope must be greater than 0. If a function is decreasing, the tangent slope must be less than 0. How does this relate to the derivative? Here it is in fancy terms, even though it's not a fancy concept. If f prime is greater than 0, then the function is increasing on that interval. If f prime is less than 0, then the function is decreasing. That simple. Example, which is, that one's tough to read, so I'll switch to the one that's a little easier to read. I think it's this one that you can read a little easier starting right there. I think this is all the same stuff that's in yours, maybe a different step in the algebra, but covers the same things. It's this simple, really, for finding intervals of increase and decrease. You find the derivative. Of course you find the derivative. You go f prime. And actually, they don't beat you to death with derivatives in this chapter. You know, in this tough derivative section, in some of these chain rule questions, we beat you with derivatives. We go every little situation, every weird fraction or anything like that. Here it's like, oh, x squared minus 2x plus 3. Yeah? It's more about the idea than the algebra now. So we go, okay, take the derivative, 2x minus 2, and find out when that derivative equals 0. If you're like, why do you want to know when the derivative equals 0? Well, when you go from positive tangent slope to negative tangent slope, there's got to be a 0 in between. 0 is the break between positives and negatives. So let's find out where all the breaks are between positive and negatives. So we set g prime equal to 0. Oh, for you physics people. We're finding out when the velocity is equal to 0, so we can find out when it. So set it equal to 0 and solve for the x value in question. This one was pretty simple, and I factored it only because we're on a common factoring binge here. And I want you to see more and more about common factoring and what an advantage it is. See, once you have the common factor, it's easy to see what the answer is. X equals 1. Now, an old friend, one of these interval charts to go, okay, I know that it's 0 here. So before 0, it must be either positive or negative. And then after 0, it must be either positive or negative. So I build a chart and I go, okay, let's check before 1. And we'll check after 1 to see what happens to the derivative. And you can see the test values I used. Your chart might not have test values in there. But hopefully, when I show it to you, you're either going to be like, oh, I can do this. I don't need your little test values. I can work it out myself. Or maybe you're going to write this down in your chart. So I said, there's the derivative, 2 bracket x minus 1. A number less than 1 is 0. And if I sub 0 into this, I get positive, and I get negative, and positive times negative is negative. Do you remember this table thinking? It's the only thing that, yeah, this was okay. I'm still going to map through it, but maybe I'll go a little faster because you're like, yeah, we got that. For x greater than 1, I used a test value of 5, but anything greater than 1 will work. And I put it in, I go, okay, 2 will be positive, 5 minus 1 will be positive, I get positive in here. That was the end of our thinking before. We go, okay, the function's negative or it's positive. But here, it's a derivative that's positive or negative. So in the derivative charts, we're going to write something underneath that immediately. When it says negative derivative, we know that's decreasing. When it says positive derivative, we know that's increasing. That's what the first part of this lesson said. So now we can make our final statement. Whatever this function is, it's decreasing when x is less than 1 and increasing when x is greater than 1. And I did it with interval notation so you could see the interval notation as well. If the grade 10s saw this example, they would puke. Because right now they're completing the square on these things to find the derivative. Or to find the max mins. Now, what they have to understand is that, yes, for this particular function, the derivative is pretty straightforward, but the derivative can handle anything. You know, where complete the square only handles squares, really. Well, it handles even ones as long as there's a certain type of even ones, but that doesn't matter. The derivative is much more powerful because any degree function is going to be pretty straightforward for us now. Here's this afternoon's lesson, right here, right in this moment. If we go from decreasing x less than 1 to increasing x greater than 1, what's happening at x equal 1? Yeah, we go decreasing to increasing. We must have a minimum there. That's all I'm going to talk about this afternoon. Really. Yeah, I'm going to expand on that a little bit, but that's the big point of this afternoon's lesson. So conceptually, pretty straightforward. Yeah? Questions on number 1? All I'm going to do now is do it with greater degrees. I don't think this factoring's shown on yours. So if the factoring's a problem for you, then get this version of the note and write down the factoring part of it. I don't want to get distracted by the factoring part of it. I'll talk about it in just a second what I mean. Okay, they give you a nasty function. Nasty. They love doing this in this chapter. They're addicted to this, putting these fractions in there that are so intimidating. Oh no, fractions. And then they're the exact numbers you need to make it so that your derivative has no fractions. See, take a look at this one. Derivative of x squared over 4. You're bringing a 4 down to multiply by 4, and there's a divide by 4 right there. How nice is that? Yeah? Sort of calculus kindness for once in the algebra. And so that's why I get x cubed there. Next one, 2x cubed. I get negative 6x squared. 5 halves x squared. See, you bring down the 2, and it's exactly what you need to cancel with the 2 that's there. It's so kind. and you end up with 5. And then the derivative of 12x is 12. Any questions about the derivative? I'm not trying to rush this just because you have a completed version. Is the derivative okay? Some of you are like, yeah, compared to what I was doing last night, that's a complete joke. Yeah, it's great stuff. And you'll find this chapter sort of like that. The derivatives won't be ridiculous all the time. Yeah? So, our goal, though, is to find out when the derivative is greater and less than 0. So our first step in doing that is find out when the derivative is equal to 0. That'll divide up our answer into positives and negatives. And then there's the factoring there. And if you're like, yeah, I can factor a cubic, did a zillion of those last in advanced functions like that, then great. You probably don't even need to write all those steps down. But if you're like, yeah, I don't know about factoring too much, then, hey, boy, you're going to have to get that nailed back down here, okay? Do you want me to talk about the steps of factoring? Who wants me to talk about the steps of factoring? You're like, no, I'm good at factoring. How many people are like, yeah, I'm pretty good at factoring? Okay, here's the quick overview. I'll split it down the middle. Quick overview. You just start subbing in numbers into this thing when you want to factor it. P at 1, P at negative 1, whatever. And when you get a 0, you use that to do your satanic division here. This synthetic division here. And then I've reduced the degree. When you get down to degree 2, you just factor it using your old ways. Or quadratic formula. Sometimes there's a cruel one where you got to use quadratic formula to get those last 2 zeros. And then use that to build the big chart. The derivative is 0 at negative 1, 3, and 4. So those are the dividing spots between negative and positive. Build the whole chart. Do the whole chart thinking. If you need more help in the charts, you just let me know. Let's talk about the conclusion from the charts. For x less than negative 1, the derivative's negative, which means it must be decreasing. Between negative 1 and 3, the derivative's positive, which means it must be the derivative's positive, so it's increasing. Between 3 and 4, the derivative's negative, so that means decreasing. See how I write increasing, decreasing, increasing, decreasing under there? It really helps me to write those things. I encourage you to, every time you build a derivative chart, to immediately write under the negative whether you're decreasing or increasing. And for x greater than 4, we're increasing. So, where is it decreasing? X less than negative 1, and between 3 and 4. Where is it increasing? Between negative 1 and 3, and x greater than 4. I think your version of it has none of the factoring in it. Is that right? So, if you need the factoring, I'll put this version of the note online so you can get that. Here, I'll jump ahead to this afternoon's lesson. Here it comes. If we're decreasing for x less than negative 1, and then notice I've made my hand do decreasing, and I'm increasing after negative 1, what's happening at negative 1? Josiah? Minimum. Yeah? No big deal. Huh? It's only the algebra that's scary here, not the idea. The idea is pretty straightforward because of the way we've built it over the last 2 courses. Then increasing to decreasing, maximum, decreasing to increasing, back to another minimum. Boy, we could really draw this function now, eh? We almost can, decreasing first. It'll be really straightforward to get all those things on there. And we're going to tie that all together in chapter 6. So that's what you'll come back to in February, which I think the timing of that is very good because you're going to have to do a little bit of derivatives, bring it all back together for one more chapter before we move on to other stuff. Questions about that example? Is there one more? Am I right? There's one more? A slightly tougher derivative. Oh my goodness. What happened here? Can I grab that? Oh yeah. Oh, that's better. Yeah, it wasn't so bad. I don't know what got in there. Yeah. All right. X over x squared plus 1? Is it the right function?
Oh yeah, for 4.
Number 4, it's right? I'm just making sure these 2 notes match up. Okay. The steps are pretty clear here. For intervals of increase and decrease, and I'm going to get the steps on there because I don't want you to get confused by all the algebra here. Set the derivative equal to 0 is step 1. Well, finding the derivative will be step 1, I guess. Here, there's a step. Find derivative. Step 2, set it equal to 0. Step 3, build the chart. Step 4, make conclusions. That's what finding maxes and mins. Ooh, look at me saying max and mins already. Because it's increasing, decreasing. That's good information. But the max mins, that's the great information that we'll find out this afternoon. Okay, so step 1, find the derivative. I hope that you look at this And comparatively speaking, to some of the stuff you're doing in the homework, you look at this derivative and go, okay, so this isn't so bad. But I'll walk through. Derivative of derivative of the top times the bottom, minus derivative of the bottom times the top, all over the bottom squared. Simplify, no common factoring even here really in the derivative, and I get down to this. But notice now, this is the first time you'll see why they factor it out the way they do in the homework, to get it ready to easily find the zeros. That's what the plan is. Not just to find the derivative, because finding the derivative by itself is virtually useless. Let me say that again. I don't want to freak you out. But finding derivatives by itself is virtually useless. Taking the derivative and doing something with it is all powerful in mathematics, like all powerful. So here we're taking the derivative and setting it to 0 because we want to find out those max and mins. It's perfect. Way back in advanced functions, people were like, so I just supposed to just guess where the max or min is? And I was like, yeah. And then somebody followed it up with a question and said, well, how do I find the max min? I'd say, you take the derivative and set it to 0. See, it's a beautiful sentence. Means nothing to you in advanced functions because you don't know what's going to happen with derivative. Now that you know the derivative, it's so simple. Finding max mins, take the derivative, set it to 0. I'm going to say that 1,000 times in chapter 5. Every time it says max min, I'll go, okay, take the derivative, set it to 0. Take the derivative, set it to 0. Take the derivative, set it to 0. We'll keep doing that over and over again. Couple of fine points here, though. Factoring when there's a negative on the first term, just factor the negative up front. It's all going to work out better for you. So see, I saw negative x squared plus 1. Little management issue that maybe you haven't seen a lot of is when you got a negative out there, factor it out because then it's easier to see what you have there, and that one happens to be a difference of squares. Okay, lots of different types of factoring coming here in this chapter. So then I get my two zeros, 1 and negative 1. I also should check the denominator to see if there's spots where the derivative doesn't exist, because that can cause me problems. Do you remember in advanced functions we had to put on the chart, we also had to put asymptotes on our interval charts? The same is true here. But this one doesn't have any. X squared plus 1 never does equal 0. X squared plus 1 is always positive, so that never does equal 0. So in my chart, I only need 1 and negative 1. This function goes from decreasing to increasing to decreasing. I used all the pieces of the derivative there. So what's happening here? Decreasing to increasing. There's a minimum there. Increasing to decreasing, there's a maximum there. So the fact that it was a quotient rule doesn't really change the whole game really all that much. Makes the derivative a little harder, but the game's still the same. Take the derivative, set it to 0, build the chart. Do you have questions on this example? It feels rushed to me because you got the completed version. I don't want it to be rushed. I want to explain it if you want. Oh, and by the way, in red here, I dealt with the denominator because the denominator does come up sometimes. Yeah? Got to deal with the zeros of the denominator. When you build a chart, zeros the numerator and zeros of the denominator. Both those zeros. Zeros and where it doesn't exist. What questions do you have? Here, hit me with some questions. It's good? Nodding?